Hello everyone. I will be presenting our paper GAVI, a category-aware generative approach for brand value identification. I'm a PhD student in the University of Bolzano, and this is a combined work with people from Wonderflow and Trento. So this will be the outline of the presentation. We'll start with a brief introduction, then we will talk about the problem definition, the proposed method, then we will talk about the experimental results, and finally the conclusion. Brands are important in e-commerce platforms. So brands are the most important attributes when it comes to products. And when we talk about products, we're talking about products on online e-commerce websites like Amazon, for example, because they help to build customers. They help customers build knowledge about other product attributes. So for this is a screenshot of a product from Amazon, for example. And by knowing the brand, we can get more information about the product. Like, for example, this product is normally organic. It is made for frizzy or curly hair, if, for example, for the shampoo product, and it's also designed for women. So there's high correlation between brands and product attributes. And this signals the signification of extracting brand values from product descriptions. So identifying brands from product description is the process of given a textual description, we would like to identify the brand inside the description. So this falls under the umbrella of product attribute value extraction. And product attribute value extraction in general is the process of processing text inside the e-commerce websites and extracting a set of attributes and their values. Well, actually, given the attribute, we would like to extract the value for that attribute. So for the screenshot of the product on the left, we would like to extract this table, which says what is the brand, what is the skin type, what is the scent for this product, and also the quantity. So we distinguish two types of products. One where the brand name is actually mentioned inside the product description, like Miel Organics in this case, in this example. And another where the text indicates the brand, but the brand is not directly mentioned. So a typical model would extract something like Moroccan argan as a brand, but the actual brand of this product from the website is Pure Nature. So why is brand name extraction difficult? Well, first because it particularly emphasizes the problem of open world, which means that we cannot actually build, let's say, a dictionary of all the possible brands, because brands are always being there's always new brands coming to, let's say, to the electronics products in Amazon. Also because of the diversity of textual semantics. So for example, if you have the word orange inside the product description, it could refer to a brand, but also to a color or also the flavor, depending maybe on the category of the product or what is the product. Also because the target brand values may sometimes be not present inside the product description, and this is what we refer to as implicit brands, like the second example we refer to here. And this is where, if we use extractive methods, they fail. Also because of the category dependency. So for example, if we have the word, if we were to build a dictionary, for example, the word sunflower could be a brand in the clothing category, but could refer to also like taste or scent inside of food categories. So here's the formal definition of the task of brand value identification. So given a product description, let's say T, which can be tokenized into a set of tokens, T1 till Tn. Also given the product category, we would like to generate a target sequence V that represents the target brand given the product description. So from the first example, given this product title, we would like to extract, and the category, we would like to generate the brand Miel Organics. So to solve this problem, we post this brand value identification problem as a generation task, more formally as a conditional sequence generation task. So we optimize the model to maximize the conditional log likelihood of the probability of the output V, which is the product, which is the brand, given the input text, the description, and the category. But in general, we factorize the log likelihood of word and subword, like in the like in typical sequence-to-sequence tasks, or like machine translation, for example. So compared to previous work, previous work on this problem use sequence tagging models. So they have open world assumption, which means that they are able to extract values not seen during training or in the training set. However, as we can see here, they cannot handle implicit brands because they are extractive, and they're also not category aware, which means that they don't take the category of the product into consideration during the extraction. So our proposed method is to employ a sequence-to-sequence model, basically a T5 model, as the backbone of our approach. This allows us to handle the first limitation of other models, which is to handle implicit brands that are not mentioned directly inside the product, and also to make the model category aware, or to take the categories of the product into consideration during the extraction. We propose to highlight the categories inside the input. So following the work of Chan et al., um, we introduce a highlight token, and then we introduce the categories inside of our input. So our input X becomes the title highlighted by the categories. And so this is an example of what would an input would look like from our previous example. So we would have the title and by highlighted by the product title highlighted with the category, or the product description highlighted with the category, and then we would like to generate the brand value as an output. So for the dataset, we use a publicly available dataset, which is called AZ Bayes or Amazon Bayes. We do two splits. One split is a random split, and the other split is a disjoint split, where we make sure that the brand values inside the test set are never seen during training. So it's basically a zero-shot experiment. There's also another set, so we do another test where we train the model on the AZ base, which is the random split, but we test it on new categories of product. So the baselines are um, the sequence tagging models that I showed in the previous slide, like BiSTM Seraph, OpenTag, which is a BiSTM Seraph model plus an attention layer on top, and then OpenBrand, which improves the generalization of OpenTag by using character level representations. We also compare with the normal T5 sequence to sequence, which is not category without category highlights. So this just takes an input the product title or description, and then our model with the category highlights. So these are the results. So these are the results on the AZ-based dataset. So this is the random split. So we can see that our approach has an overall improvement in F1 score of up to 4.1%. Also, what is interesting is that we see that both generative approaches like T5 and our approach outperform other extractive methods, which hints that using generative methods can help in identifying brands that are not present inside the description. For discovering new values, which means the zero-shot experiment where we test our models on the AZ zero-shot dataset, our model also has improvements of up to 17.1% as compared to the previous sequence tagging models. So we also do another experiment to compare between our approach and T5 to see the significance of taking categories into consideration. So we separate from the random split, we separate the instances where the brands are not mentioned directly inside the product description. So here you cannot see the extractive approaches because simply they cannot extract any value. So this resulted in 9K implicit examples from that data set. And we can see that our approach performs significantly better than the T5 because it takes the product categories into consideration. So here I show some examples of the extracted values from several products. So in the first one, we can see that, for example, the sequence tagging model would mistakenly identify the word Mitsubishi as the brand from this title, because Mitsubishi could be also a brand, but this title, the actual brand of this title is not this word. But our model is able to correctly extract it. Also, interestingly, we saw that our model is also able to uh, correct, like extract the value, but also if there is a grammatical mistake, it's able to extract it in a correct way. Probably it was because it was seen during training. And when the case is that the brand is actually mentioned inside the product description, our model is as equally good as the extractive methods. So, as a conclusion, our generative approaches perform better. We saw that T5 and our approach perform better than the extractive methods because they can identify values that are not mentioned inside the title. We also saw that taking categories into account or modeling the dependencies on the categories could also result in an improved performance for the model. Um, we also saw that model performance is category dependent, which from the tables before we can see, for example, that depending on which category of product inside the data set we are working on, the gains could be higher or lower. For example, we saw in our experiments that, for example, the results on the electronics domain or categories is better than food categories. One major limitation though of our model is that it assumes that the brand value can always be inferred. So we cannot say that. So our model cannot basically say that there is no value or cannot deduce a negative value because there was no training instances. But it's also it's also something that we plan to work to actually test because it's interesting to know because it's a generative model whether the model would be able actually to not to detect that it cannot be that the actual brand cannot be inferred from the description. So to solve this problem, we plan to extend the model to be able to detect negative values, and we also need to include negative samples inside our dataset. Finally, for reproducibility, our code and fine-tuned models can be found on GitHub. Also, we have a demo that is a web application of the model where you can actually interact with the models that we have seen here. Thank you.